Okay, I want you to forget everything you think you know about the number line. Today, we're going to decode the hidden DNA of our entire digital world, an operating system built completely out of numbers.
So think about your phone's GPS for a second. It uses these wild numbers that just go on forever, decimals that never, ever repeat, to pinpoint your exact location. I mean, how is that even possible? How can something infinite define something so perfectly, well, finite?
Well, the answer isn't magic. It's math. It's all hidden in the operating system of our reality, the number system. And listen, this is not just some chapter in a textbook. No way. This is the actual code that powers everything, from your video games to the satellites orbiting our planet right now.
So to really understand this code, we first need to build a tool. Think of it like the ultimate master ruler, a ruler that can measure absolutely anything in the universe perfectly. Let's dig in and see how it's built.
We all know this map, right? The good old number line. You start at 0, you can walk to 1, 2, 3. You can even land on fractions like 1/2 or -1/3. It seems pretty solid, pretty complete. But what if I told you there are these mysterious, invisible gaps all over the place? Holes that you just can't fill with any fraction you can think of.
Now, the numbers we can easily plot, we call those rational numbers. They're basically any number you can write as a simple fraction. You can think of them as the tidy, predictable residents of the number line. 5 is just 5 over 1, 0.5 is just 1 over 2. Simple, clean, well-behaved.
Okay, but here's where it gets really interesting. It's how these numbers act as decimals. Rational numbers, they're predictable. Their decimals either just stop, we call that terminating, or they repeat in a consistent pattern, like 0.333 forever, which we call recurring. It's like a steady beat in a song. But those other numbers, the ones that fill the gaps, the irrational ones, oh, they're the complete opposite. Their decimals go on forever and they never repeat. It's like a song with a melody that goes on for eternity and never ever repeats itself.
So, here's the big takeaway. When you take all those tidy rational numbers and you pour in all those wild irrational ones, you finally fill in all those mysterious gaps. And just like our textbook says, you create the complete collection of real numbers. There are no holes left on the number line. Our master ruler is finally complete.
And hey, if you think these irrational numbers are just some abstract idea somebody made up, just look at this spiral. It's built using simple right-angled triangles, and the length of each new side. It's an irrational number. The square root of 2, the square root of 3, and so on. They have a real physical shape. This isn't just theory.
Okay, so we know these irrational numbers are real, but that whole infinite non-repeating thing makes them kind of messy to work with, right? So how do we handle them? Let's check out how we can actually tame this infinity with a really clever math move.
So here's the kind of problem we're talking about. Look at this number, 1 divided by the square root of 2. See, having an irrational number in the denominator, that's the bottom part of the fraction, it's just messy. It makes calculations super difficult. It's like trying to build a skyscraper on a shaky, unpredictable foundation. We gotta stabilize it.
And the superpower we use to fix this is called rationalizing the denominator. Yeah, it sounds complicated, but really it's just a way of cleaning things up. We're converting the expression into an equivalent one, meaning it has the exact same value, but with a nice, stable, rational number on the bottom.
So how do we do it? It's a really simple 3-step trick. First, you spot the problem. Our shaky foundation is the square root of 2. Step 2 is the genius move. We multiply the whole fraction by the square root of 2 over the square root of 2. Now, what's any number divided by itself? It's just 1. So we're not changing the value at all, we're just changing how it looks. Finally, step 3, we simplify. The top becomes the square root of 2, and on the bottom, the square root of 2 times itself just becomes 2, a nice, solid, rational number.
And here's the proof, pulled right from the source material. You can see the whole process laid out. Our messy, unstable number, 1 over the square root of 2, gets transformed into its clean, stable twin, the square root of 2 over 2. The foundation is now solid. We've just tamed a little piece of infinity.
So why does any of this matter? Why even learn this superpower? Well, let's take a look at where this math lives out in the wild, where it's being used every single day by people in some pretty amazing jobs.
Data scientists? They need this level of precision to find patterns in billions of data points. Architects and engineers? They're using these exact calculations with square roots to make sure a bridge can handle high winds. And get this, music producers are literally manipulating digital sound waves,
which are just functions built on this very number system to create the perfect sound. It really is everywhere.
All right, we've decoded the system, we've learned how to tame it, and we've seen it out in the wild. Now, it's your turn to build. It's time to take these skills right off the page and find them in your own world. So here is your challenge. Find a perfect square in your home. Could be a floor tile, a coaster, maybe even your TV screen. I want you to carefully measure the length of one side and then measure the diagonal. Now, divide the diagonal's length by the side's length. You should get a number really close to 1.414, which is the square root of 2. Go on, try it. Prove to yourself that math isn't just in a book, it's the actual blueprint of the room you're sitting in right now.